Yeah.
We have a random question.
Okay.
If you wanted to turn our Gamoku thing into like a proper game with a user interface, what would you use?
So pie game is, I guess, what people usually use. Yeah. So yeah, I got like, so you could do pie game. You could also like again, like it also kind of depends on what you want to do, because a lot of people now would want it to be kind of web-based. And if you want it to be web-based, you would probably kind of do something in the browser. And that would be JavaScript, or like just like if you go like JavaScript games. Yeah.
Thank you.
Yeah. All right. Okay. Hi, everyone. Hello, hello. Hello. How was calculus? Okay. So, yeah, I thought it would be funny to drain my battery again and see how things go. I did bring a charger, so it's not going to be that funny. But anyways, so I want to talk just briefly about Project 2 and then introduce Project 3, which is up. So I've posted the tests that are worth the 88.5%. So most of the tests were already on Gradescope anyhow, but if you want to look at the tests, download the zip file. It's a little bit difficult to read, but you can find the test by name. So for example, you have like, test is bounded and whatever, and then you can just copy the board and you can see that here what's happening is we're calling is bounded with those arguments and stuff. Okay, so if you're stuck in a particular test, you can do it. So so those tests are the tests that were already on Gradescope from the get-go. That's nothing new. It's just to help people debug. The reason I don't post them right away is that obviously you could do that with an if statement if you really wanted to. That, for the record, is banned, like saying if board is equal to that. then, however, a technical possibility. Not allowed to do that. Do not do that. So that's kind of part of the reason that they don't do that right away, but they're there now. There's secret tests that are going to be worth the other 11.5%, but I'm not going to change those things up on you in the coming. So project 3, I give you the initial tests as usual. There's not going to be more tests for project 3 that are released publicly. As we go on in the semester, more and more we want to approximate what it looks like when you do the real thing. Of course, when you're solving a new problem, nobody gives you the tests. In fact, you could argue that coming up with tests is becoming more and more important as tools like ChatGPT are able to generate code. Because essentially one way in which people might be moving towards using ChatGPT, not in academic settings, but in general, is you come up with a good description and you come up with the test cases, and then maybe ChatGPT helps you write the code. So coming up with your own test cases arguably is becoming more and more important. Okay. So that's project 2, and acknowledging that I was like traveling and stuff like that. So I posted it kind of late. I'm giving everyone 2 free grace days that it can only be used for project 2, which is mathematically the same as, you can submit by the 19th with no consequences. Okay. Questions about Gomoku? Anything? Okay. So that's like that. So I've posted the last project just now, project 3. I want to talk about project 3 in general now, and we'll then go back to complexity. So let's talk about project 3. So project 3 is about word embeddings. So here's kind of the motivation for that. So this is the kind of test that maybe many of you had to write, like for if people wrote TOEFL, this is actually something that's kind of TOEFL style, other standardized tests as well. So you want to choose the word which best expresses the meaning of the given word. So, I've chosen something that's a little bit weird so that it's kind of interesting. So, nifty, is it like thrifty or caffeinated or groovy or shifty? So, well, nifty is the most similar to groovy if you look it up. Okay. So that's the kind of task that we want to solve. And you can, of course, solve this task just with a thesaurus, right? That's what a thesaurus is. But what we want to do, what's going on here? What we want to do, okay, it's fine. So what we want to do is try to do it automatically without the thesaurus. So maybe for words that aren't in the thesaurus, like, I don't know, what's a good new word, like mid or something. Maybe it's not in any thesaurus, okay? So, or, stuff like that. Or you want to do it for a language that's not English or something like that. Or you want to use this kind of stuff for building something like ChatGPT, which we'll talk about in a second. So one way to approach this is rather than say, I'm going to build a big database of which word is like another word, I'll just read in a bunch of text. So the kind of thing that you did for the lab last week. And then I'll use something that's called the distributional hypothesis in linguistics. The distributional hypothesis is that words are related in meaning if they appear together in similar contexts. Okay? So how do we operationalize it? How do we use this hypothesis to the extent that it's true? Well, what we'll do is we'll count up how many times does any particular word appear together with any other word in a big corpus. A corpus just means a bunch of texts, like, for example, Project Gutenberg that you used last week, right? So here's an example. So dog would probably occur together with homework quite a bit because people often say the dog ate my homework, whether because that happened or because they're joking or whatever, right? Dog would also, appear together with veterinarian quite often. It would appear with school, maybe not as often. Okay. And then we'll do it for every kind of word, and we'll say, okay, so if dog appears together with eat and it appears together with homework, then we'll represent it as this kind of vector where the number of times the dog occurs together with homework is going to be over here, and the number of times that dog appears together with eat is going to be over here, right? And then if we're talking about something like student, we'll say, okay, well, like student appears together with homework as well, quite a bit, and together with university, but students don't have time to eat, so maybe not as often. Okay, it's an example. The hope would be that something like student and scholar would, if you look at them as vectors, appear together with different words, maybe not the same amount of time, but an amount of time that's proportional to each other. Okay, so if, for example, student and scholar appear in the same contexts and in the same proportions, but maybe scholar doesn't appear as often as student in the text, what you would expect is that if you think about those words as those kinds of vectors of co-occurrences, that student and scholar point in the same direction, but the scholar vector is shorter than the student vector. Does that make sense? No? Yes? I know. Okay, so that's the idea. Looking at words as those kinds of vectors is called, the technical term for that is word embeddings. So let's look at the technical details here. So I'm going to project 3. So this is the handout that's on the course website, right? So here is how we're going. So this is, the Dostoevsky excerpt from last time as well from the lab. So this is how we're going to represent the word man as a vector, right? So using this passage, it occurs with I 3 times and with M 3 times, and then with unattractive once. Okay. This is how we are going to represent liver. So that just occurs together in the same sentence once with every word, just because liver only appears in this sentence. So by occur, we mean the two words are together in the same sentence. Make sense? So that's the representation. Now, what we had on the slide was each word was a vector. Those seem like they're not vectors that are in the same space because they are different lengths, right? But they're not really. So those are sparse vectors. This is the thing that we had before the break, right? So if you, let me open, okay, I'm not gonna do this. So if we look at it like this, what we can do is we can say, okay, so we have man and we have liver. And then we have the co-occurrence counts, right? And the concurrence count would be with I and M and ah and sick and spiteful and N and unattractive, as well as with believe. So I skipped the I because that was already here. And with my and is and deceased. And now we can just fill this in, right? So I here is 3, M is 3, A is 2, sick is 1, spiteful is 1, N is 1, unattractive is 1. And then believe, so man does not concur with believe, so that's just a 0. And then does not concur with my, so that's a 0. Does not concur with is, and does not concur with deceased. On the other hand, liver occurs with I once, not anything with 0, not anything with A, not anything with sick, not with spiteful, not with an, not with an attractive, but one was believe, once was mine, is deceased, right? So if we look at concurrences this way, we can in fact represent words as fixed dimensional vectors. Does that make sense? Questions about this? Yeah.
So, when we're looking at it like this way, we took man and liver out of the sentence because we're comparing them to that.
So we're not taking them out of sentences. We're saying for each word. So here the example was for liver and man, but we'll also have something for spiteful, right? And we'll also have something for believe. And for each of those, we can construct an n-dimensional vector. The n-dimensional vector would be the vector of all the concurrences with all the words. Make sense?
But like, you took out the word, like, if I am a sick man, right, is the sentence, right? So how come man isn't in that sentence? Or
No, like there, it's all in the sentence. So like we're looking at all of this as the input, right? We are taking the entire text, and then we're saying in this text, how many times does man occur with every other word, right? Does that make sense now? Okay. So here, so this is going to be a little bit longer, right? So there's more different words in even this passage, and certainly more words in the novel as a whole, right? But what you can do is you can construct an n-dimensional vector that corresponds to each word in the corpus. So corpus, again, the entire input, where n is the number of distinct words in the corpus. We're not doing it explicitly, because if we do it explicitly, so the number of words in the corpus, depending on how you count, is going to be like in the tens of thousands. So if you construct all of those, that's going to be like 10,000 squared, so 100 million. Not anything that you can't do, but kind of annoying. So what we do instead is we store those vectors as sparse vectors using dictionaries. So like this. Make sense? So now that we're here, let's go back to the graph. So here we are kind of pretending that the vectors are three-dimensional. So we're just looking at co-occurrences with university and homework and eat. And then the hypothesis here would be that words that have similar meanings are going to be close together in this is called embedding space. Make sense? So we're hoping that something like scholar and something like student are going to be similar vectors, whereas something like scholar and something like dog are going to be very different vectors. Yes.
It's like their components are the same. They're similar.
So that is because we are, according to the distributional hypothesis, words that have similar meaning occur in similar contexts. Okay, so the intuition here would be that scholar and student basically occur in the same proportions with university and homework, approximately. That's not like a mathematical truth. That's just an intuition for what we're doing. Make sense? So now we need to actually operationalize it. So what we are looking for is we have, remember, an input, kind of like that. And we want to say, well, which word is Nifty the most similar to? So let's say, guys, you're having way too much fun. It's distracting. Share with the class. Anyway, okay. What's going on in Discord, by the way, is, well, that's not fun. Okay. So how are we going to compute like how similar is Nifty to Thrifty? How similar is it to caffeinated and so on? So what we can do is, again, going back to the handout, is compute, for example, the angle between the vectors. So if we want to know how similar are the vectors u and v, we'll compute the angle, or more precisely, the cosine of the angle, and we'll compute that using the cosine law, right? So if you remember this, how many people know that this is the cosine of the angle between u and v? Some people. It is. Right? So that's just the cosine law. I'm not going to prove it. You can look it up, but this is the cosine of the angle between u and v, right? We refer to it as the cosine. We refer to it as the cosine similarity, and the idea would be that, you know, if the angle is 0, the cosine is approximately 1. If the angle is large, then the cosine is, you know, further away from 1. All right. So we have those vectors. They look like this. You can compute the dot product. You can compute the norm. That means you can compute the similarity. All right. So at this point, it's worth pointing out, the angle is not the only thing that you can do. So what's another way of kind of figuring out whether the scholar vector is similar to the student vector? That's not the angle. Anyone? Yeah.
Like find what the distance is between like the back.
Yeah, the distance between the endpoints, exactly. So you could just say, like, you know, what's the distance between scholar and student? And the fact of the matter is, that's also a valid way to do it. You can do it. It doesn't work that much worse. But does anyone have an intuition for why you might? So I actually mentioned it in passing a couple of minutes ago. But why might you prefer the angle to computing the distance between the endpoints? It's not an obvious kind of thing. Yeah, you have an idea? No? Anyone? Yeah.
Because like you're looking for if the ratio is the same.
Yeah,
or
yeah.
if, like one is like way less common.
Yeah.
If it has the same ratio, it's gonna be like.
Exactly. Yeah, that's exactly right. So it's the scholar and student example. So student is a much more common word than scholar. And it might be that, in fact, you hope for the angle to be small, that the ratio between how often it appears together with university and how often it appears together with homework is kind of the same for student and scholar. That's what it means for them to point in the same direction. It might be that one of the vectors is much shorter than the other. So the distance between the endpoints might not work well in this case. You might go back and say, well, like just divide by the norm first, and then they'll be the same lengths. And that's a valid point if you made it. Okay, so there's different ways of getting at how similar the vectors are. Which one works the best is an empirical question. So for project 3, what you're doing is what I described so far. So you are computing the word vectors for every candidate word. And then for this kind of task, you're reading in the file and you're asking how similar in this embedding space is the candidate word to every one of the possibilities. Pick the possibility that's as close as possible to the target word, and that's your guess. It's not going to work every time, but it works surprisingly well. Yeah, so won't you need a huge text? Yeah, you would, and yeah, as the person pointing out. So I picked out like 2 famously long novels. So War and Peace and Swan's Way are like famously very long. So so like Swan's Way is like the first part of Remembrance of Things Past, which is the long thing. Swan's Way is like not. It's like a slim volume. But anyway, yeah, it's they are long enough that if you add more, like there's diminishing returns to adding more text using this method. Of course, like if you're using something more fancy, like people are doing now, you need, longer, longer texts. Okay. So, all right. So, a few kind of bigger picture things that I just want to quickly mention before we go back to complexity. So this idea of embeddings came up, pretty recently, all things considered. So word2vec is the big thing that people have come up with about 10 years ago, I would say. And this does not work, to be clear, with the embeddings that you're computing. This is fancier than that. But people have started noticing with this more fancy way of computing embeddings, which is kind of what I did, but not quite, is you get all sorts of things that you did not encode into it, but it just falls out of trying to come up with really good embeddings. So with word2vec, what people noticed is that in this, this is just a picture, it's not really 3D. Word2vec is like 1000 dimensional, but people noticed that, the line from king to queen in this embedding space is kind of parallel to the line from man to woman. And that's not encoded. It's just in the way that people compute word2vec, it just turns out to implicitly be the case because that's how people use the words. And that kind of means that, like if you want to get at approximately the vector for king, you can get to it from the vector for queen by adding like the difference between the vector for man minus the vector for woman. So similarly for conjugating verbs, similarly for kind of countries and capitals and stuff like that. So that is something that people noticed. Again, to be clear, will not work with the simple way that we're doing it, but will work with a slightly more complicated thing. So I wanted to also put this in the context of what we were talking about when we were talking about Jeff Hinton's work and Hopfield networks. Share. So the big idea, so what really made, in a way, language models work is exactly what we're doing in Project 3. It's computing vectors that represent in some way, in some sense, the meaning of the input. So if you remember, what we did with Hopfield networks is we're trying to store multiple memories. And the way we're doing it is by figuring out a fixed set of weights that would encode multiple memories, multiple vectors. And there was this special way of doing it where, you know, like the way you would encode the vectors is it's the minimum of this energy function, right? What we've just discussed is also a way of trying to come up with representations for words that are fixed dimensional vectors that would be useful for some kind of downstream task. So in this case, finite synonyms. So word embeddings in general, so n-dimensional vectors that correspond to words, are kind of an intermediate step to transformers. So transformers is kind of the T in GPT, right? GPT does use word embeddings, kind of, so not quite in the, they're not computed manually, they're still word embeddings. So what GPT does, though, in addition to just literally using word embeddings that are implicitly computed, is it computes the n-dimensional vector that represents the meaning of a text up to the kth letter in the input. So essentially, and maybe we'll talk about it in an optional lecture, what GPT does is computes this n-dimensional vector that represents the meaning or something like the meaning up to now. And from that n-dimensional vector, it predicts the next word and then the next word and the next word. That's transformers. Don't you wish you knew that 5 years ago you could make $1 billion? So, okay. So that's that. There is a connection between Project 3 and computational complexity, but I want to get to that on Wednesday instead, when I've done a little bit more computational complexity, but you can start Project 3 right away. There's no problem. Okay. I will take some questions if there are any. Otherwise, I'm moving to complexity. Someone save people from complexity. Yes.
Are you going to learn how to make something like ChatGPT in this course? Or?
No. Sorry. So the question was like, am I going to teach you how to build ChatGPT? No, that's like Anxi first year, second semester. Just kidding. So kind of, it's, you know, second semester, third year of machine intelligence in a sense, right? So kind of a big part of what goes into building ChatGPT is actually kind of scaling things up and, you know, figuring out how to build a big data center and figuring out how to actually implement the thing. The principle of how to build a transformer that's completely accessible, it happens that it's taught, you know, slightly in first semester, third year, and then in more detail in third year, second semester. You could teach it if you wanted to, you know, after people are done with calculus, you know, you could teach it next semester if you really wanted to. Yeah.
Here and just like give it definition, sort of ranges, and that they're deep.
It's more complicated than that. So deep refers to the depth of the neural network, which is not something that has come up so far. So I'll do at some point this year, hopefully this semester, if not the next semester, I'll do a lecture that kind of explains things in more detail. Happy to talk about it after lecture as well. Okay. All right. I will be going back to computational complexity. Sorry, so questions about Project 3 or anything? All right. So let's go back to computational complexity. So I'll start with, again, find E, that's just the linear search. And I want to point out, so if you go to the calendar, I wrote up the computational complexity notes. So I will do things kind of like on the Blackboard, except I'm going to type because a lot of people are watching the recording or watching the live thing or something. But the notes are also here. So if you prefer to read something that's kind of like linear, then I got you. Okay. So we're going back to find E. And what we're doing is we're saying, for I in range length L, so that's the same as before. If L at I is equal to E, return I, and otherwise we return -1. So that's the same thing as before. So now, what we were saying before, just before I disconnected and went to the beach, I did not. I went back to the conference center, is what do we want to measure here? So what we want to ask is, so to measure how efficient the function is, we want to ask, in the worst case, so if we don't return early, what is the runtime proportional to? The reason we want to ask what is the runtime proportional to is that on different computers, this is going to take different amounts of time. And like just looking at the code, I cannot say, well, like this is going to take 10 seconds. That's not something that makes sense, right? What does make sense is to say, well, if I need to run this, it's going to have to run for length of L iterations. And on every computer, an iteration is going to take some constant amount of time. So the runtime as a whole is going to be proportional, in this case, to length of L. Does that make sense? So why is that the sensible thing to do? Well, because really what we care about, in addition to just not being able to answer the question of like how many seconds is it going to take, because it's going to take different amounts on different computers, it's also the case that if the runtime is proportional to, for example, log n, then the fact that it's proportional to log n rather than n is much more important than what it is exactly, right? Because, like we said, imagine that for linear search, so this is linear search. Even if runtime, so this is hypothetical. Let's say it's like 0.1 times n, and let's say that for binary search, depends on the units, like milliseconds or something. So this is different made up numbers from before. Let's say that the runtime is like this much. It's still the case that binary search is much better. And that's because when it really matters, so when the input is large, this is going to be still smaller than this. And that's because n grows much faster than log n. So that was the point of the example from last time. Does that point make sense? Questions? So, okay. So the way we write it is we say the worst case runtime complexity, it's asymptotic. Is O of n for n equals to length of L. So what does it mean? It means that approximately for large n, the runtime is going to be proportional to n, where n is equal to length of L. That is most of what you need to know. However, given that this is Anxi and I have a whole 8 minutes, I'm going to give you a rigorous definition of O of n right now. Yes.
Wondering, like, are there cases where, like, even though the worst case runtime of one function is more than another, on average, like, one function works faster, and like, is the worst case runtime good? Like, is it a good measure for every single?
Yeah. So the question was, I was talking about worst case runtime, but you could imagine, well, like, why are we talking about worst case? Maybe what you care about is what is it on average? Are there such cases? The answer is yes, there are such cases. So in fact, when we'll get to analyzing runtimes when using dictionaries, on average, access for an element in the dictionary is O of 1, but in the worst case, accessing an element in the dictionary is actually O of n, where n is the number of elements in the dictionary, for example, right? So in that case, it matters a great deal what the average case is. It also matters what the worst case is, but the average case is arguably more important, right? So, however, in many cases, the worst case runtime complexity is just proportional to the average case runtime complexity. Not in all cases. So there are exceptions, like dictionaries. In fact, dictionaries would be the big example where it's true. If for all the other things that we see, it's not true. And let me give you an argument for why this might be the case. So let's say that we're looking at linear search, right? So on average, how many iterations is that going to take? Give a stab at it. Yeah, like about half, like more or less, right? But n over 2 is proportional to n, so it doesn't matter, right? So in the case of linear search, that's the argument. Yes, like it's going to be on average about half. There is like a subtlety there, which is that, well, it's about half if the element is there. If the element is not there, it's definitely n, right? And what is it going to be exactly? Well, that depends on how often do you call it when the element is there versus how often do you call it when the element is not there. There's further subtleties about like, is it like sorted, stuff like that. But in many cases, it just turns out that the worst case is just the same as the average case up to a multiplicative constant. Not always. Yeah. Okay. All right. 5 minutes. Rigorous definition of O of n. All right. So I'm going to use kind of the standard notation. I'm going to translate it to what you've seen in calculus in a second. So G of n is O of f of n if lim sup as n goes to infinity of G of n divided by f of n is smaller than a constant. So informally, G grows at most as fast as f. Okay, so lim sup is something that I'll define in a second, but for now, ignore the soup. just think about the lim. So if n goes to infinity, what we're saying is that this ratio cannot become infinity. If the ratio of g of n to f of n grows and grows and grows, that means that g actually grows faster than f. Okay? So what we're saying is g grows at most as fast as f, so that means that the ratio g of n, f of n does not go to infinity. So the soup, soup is AKA least upper bound. So what lem soup is, and this I'll leave you to read about it if you really want. Like for this class, I just want to focus on the lem. So really lem soup is H is the limit as n goes to infinity of the least upper. So soup is the greatest lower, is the least upper bound. So this is what you use, I think, in calculus of h of k for k greater than n. All right. So that's the definition. You can't say I wasn't rigorous about it. I'm not gonna test you on this. The reason it's like that is because if you just do the limit might not exist. So you might have g of n that's approximately f of n, but if the ratio kind of oscillates, then there is never a limit. Right? So imagine like g is sine and f is cosine. So g is like sine and f is cosine. The ratio is going to oscillate. They're both actually limited to between -1 and 1. So you want for this kind of thing to exist, and the lem soup makes it more robust, essentially. If you don't understand this, this is fine. Okay? So that's the formal definition. And what's G, what's F? I have 1 minute left. So in this case, what we're saying is that the runtime is G of n. So the runtime for input of size n. And then f of n is the complexity. And what we're saying is I want to say all of n, and that means that the ratio of the actual worst case runtime to n is going to not go to infinity. So that is what the rigorous definition of this is. The non-rigorous definition is just the runtime is proportional to whatever this is. Yeah. O of it, this is O. Okay, so that's that. And what I mean by that is this. So this is the formal definition. And the informal definition is this. Okay, so O stands for order. And that's like people say, like on the order of. Okay. All right. See you on Wednesday. Bye.